Hello everyone, welcome back you all in this new video where we are going to see manual approach for the design of beam for the combined effect of shear, bending moment and torsion. This complete problem we are going to solve in 5 important steps. In the first step we will see the complete problem statements along with the determination of type of section to be designed as singly reinforced and doubly reinforced. In the second step we will see how to calculate the equivalent shear force and bending moment as per IS 456-2000. In the third step, we will see how to design for flexure and calculating the flexural reinforcements. In the fourth step, we will see how to design for shear and calculating the shear reinforcements. And in the fifth step, we will see how to prepare final schedule and details according to the design results. For better understanding of everything, you have to watch this video till the end. And if you are interested in the field of structural design and you are new on this channel, so we are continuously uploading this kind of videos. So please subscribe this channel and share this video with all of your friends and press the bell icon to get every notification. First of all, try to understand the problem statement. So here we have to design a simply supported beam which is having the effective span of 4.3 meter. And the section size of this beam has given as 230 by 550 in mm. This beam is subjected to working moment of 101 kN meter and working shear force as 41 kN and the twisting moment as of 18 kN meter. We have to design this beam with a grade of concrete as M25 and grade of steel as Fe500. So let's start the solution. So first of all, we would like to write the given data. So here the data has given as section size of the beam. So we know that width of the beam as given 230 mm and overall depth of the beam as given as 550. So these two dimensions are actually sectional dimension. Look at this figure. So here this is the beam section where this is actually the width of the beam and this is overall depth of the beam. Two dimensions are actually given. In addition to these two dimensions, one more dimension has given as effective span of the beam. So this effective span of the beam given as 4.3 meter. Now I would like to write material properties. So what is the material property? The material property has given as M25. So 25 is the characteristic strength of concrete and grade of steel as given Fe500. So yield strength of this steel is going to become 500 MPa. Now analysis results are moment equal to 101 kilonewton meter. So this is the service bending moment, service shear force and service torsional movement. All these three things are actually given here, but they all are working in service values. We actually have to use factored value for the design purpose. So that's why we need to multiply these all values with 1.5 so that we are getting ultimate moment as 151.5 kilonewton meter, ultimate shear force as 61.5 and ultimate torsional movement as 27 kilonewton meter. After multiplication of 1.5 factor with all these basic values of service loads, we have to proceed further with some assumptions. What are those assumptions? Try to understand. So here we have to assume the clear cover for the beam. So what does mean by the clear cover? Here with this figure, try to understand what does mean by the clear cover. So this is actually the overall depth of the beam and clear cover from the face of the shear reinforcement. This is what the shear reinforcement. This is actually the shear reinforcement. So from the face of the shear reinforcement up to the edge of the beam, this is called as clear cover. We would like to find effective depth. And what does mean by the effective depth? Effective depth from the top edge up to the center of the main reinforcement. So to calculate this effective depth, we need to know the diameter of main reinforcement. We need to know the diameter of shear reinforcement. So right now we don't have any value for this main reinforcement, for the shear reinforcement. That's why what we need to do, we need to assume the diameters. So here I am going to assume the diameter of main reinforcement as 20 mm. That may be changed on later stage after the design. This is what diameter of shear reinforcement. It is going to become what? 10 mm. I am going to put all this value here. So what is the formula? The formula for calculating the effective depth will equal to overall depth. This is what? Overall depth minus this clear cover minus this diameter of shear reinforcement minus half of this diameter of main reinforcement. So this is the formula for calculating the effective depth. So this formula I am going to apply in this problem. So we are getting the effective depth of the beam. So effective depth will equal to overall depth minus clear cover minus shear reinforcement minus half of the diameter of main reinforcement. So we are getting actually the effective depth available of this beam as 505 mm. In the first step, we have to decide the type of section to be designed as singly reinforced or doubly reinforced. Here it is important to understand what does mean by the singly reinforced section and doubly reinforced section. So a section in which there is a presence of the main reinforcement or design reinforcement, or in another way we can say that flexural reinforcement at the bottom face, and there will be no requirement of the design reinforcement at the top face. For the case of simply supported beam, at that time that section we are going to call it as singly reinforced section. You may say that there is a presence of the main reinforcement. How we can say that there is no reinforcement on the top side? So actually this is what the minimum requirement were made by ISSP 34. This code has recommended that in any section of the beam there should be minimum number of bars should be present as 2 at its top, at its bottom. So actually there is a presence of 2 bars. It is just to satisfy the minimum requirement. It is not the design requirement to provide this 2 number of bars. And at the bottom face there is what? This is the design requirement. This is the main reinforcement required, and accordingly we have provided at the bottom. So this is called a singly reinforced section. And when we are providing this singly reinforced section, when your ultimate movement, whatever the movement coming to your beam, that ultimate movement is less than the capacity of this section to carry the movement. What is the limiting capacity of this movement? So that is called as MU limiting. So if this condition is going to be satisfied, at that time we are going to design the singly reinforced section. It means that there is need to provide the reinforcement at the bottom face only. In another situation, when your ultimate movement is beyond of limiting capacity, beyond the movement resisting capacity, at that time we have to provide the doubly reinforced section. So there will be the presence of main reinforcement at the bottom face, as well as there is the presence of main reinforcement at the top face. So this is called as doubly reinforced section. This is called as singly reinforced section. So in our proposed example, we need to find out either we have to design the singly reinforced section or we have to design the doubly reinforced section. That we will decide first. So here the ultimate moment is 151.5 kilonewton meter. So this is what the ultimate moment we earlier have calculated by taking the factor value as 1.5 over the service moment. So we are getting the factor bending moment that is coming to your beam as 151.5. So we have to compare this ultimate moment with the moment resisting capacity. Now from where this moment resisting capacity will come? So this moment resisting capacity will come from your IS 456 2000. So that IS 456 2000 has suggested that for Fe 415 MU limiting is going to become 0.138 FCK BD square, and for Fe 500 MU limiting is going to become 0.133 FCK BD square. So this is what the formula. So I am going to use this formula to find out what is the capacity of this section to carry the moment. So 0.133 FCK B into D square. So where 0.133 multiplied by 25 characteristic strength of concrete multiplied by width of the beam 230 multiplied by effective depth square. How much the effective depth? Let me check that. So it is 505. So that I am going to put here as 505. So you are getting the value as 195.03 kilonewton meter. So this is the capacity of your section, and this much intensity of the movement is coming to your section. So whatever the load is coming, that is 151 and capacity is 195. So action is less than the capacity. So your ultimate movement that is coming externally, which is less than the capacity of the section, hence it is needed to design as singly reinforced section. But in a situation when MU is going to become more than that of MU limiting, at that time we have to call, here it is needed to design doubly reinforced section. Now next, after that we have to find out the equivalent shear force and bending moment as per IS 456 2000 clause number 41.3. But before of that, try to understand why it is needed to calculate the equivalent shear force. So in our proposed example, actually your beam is not subjected to purely movement and purely shear force, but also there is a presence of torsional moment. So IS 456-2000 has suggested that in a situation when your beam is subjected to torsion in addition to ultimate moment, in addition to shear force, so at that time you have to consider the effect of torsion. You have to consider the effect of torsion in shear force as well as in moment. So where it is given, look at IS 456-2000 41.3 clause shear and torsion. So when you are going to design your beam for the shear force, so the basic shear force, ultimate shear force will not be enough to design. You have to add the value of torsional effect 1.6 multiplied by torsional movement divided by width of the beam. By this formula, you have to find out equivalent shear force. Once you get the equivalent shear force, then also you have to find out the equivalent bending moment. So that equivalent bending moment will be equal to your basic ultimate moment plus moment due to torsion. And how to calculate the moment due to torsion, that is also here it is given. So this all calculation, all these formulas are actually considered in this calculation. So first of all, we are going to find out the equivalent shear force. So basic shear force plus shear force due to torsional effect. So if you are going to put the value for this shear force due to torsional effect, so combined formula becoming like this. Okay, put all the values. Ultimate shear force is 61.5 plus 1.6 multiplied by ultimate torsion 27 divided by width of your beam in meter. So it is going to become 0.23. So finally we are getting the equivalent shear force as 249.326 kilonewton. Thereafter, we also have to calculate the equivalent moment. So equivalent moment is actually equal to basic moment plus torsional movement. So I would like to calculate the torsional movement first. So the formula for calculating the torsional movement is TU divided by 1.7 multiplied by 1 plus capital D divided by B. Capital D is your overall depth divided by width of the beam. So when you are going to put all these values here, you are getting the moment due to torsional effect is going to become 53.86 kilonewton meter. Here, one more thing were specified by the code IS 456 and clause 41.4.2.1. What this code is suggesting, when this torsional movement is less than ultimate movement, at that time there is no need to provide the compression reinforcement, means reinforcement at the top. So earlier we have seen a criteria mu comparison with mu limiting. When mu is less than mu limiting, at that time singly reinforced. When mu is greater than mu limiting, at that time doubly reinforced section you have to design. But one more criteria given by your IS 456 clause number 41.4.2.1, when your beam is subjected to torsion, in that situation you have to compare this ultimate movement with the torsional movement also. So in a situation when torsional movement is less than ultimate movement, in that case there is no need to provide the reinforcement on compression side on the top. But in a situation when torsional movement is going to become more than that of your ultimate movement, at that time we need to provide the reinforcement on the compression side. So that things you have to keep in your mind. So equivalent movement is going to become what? Ultimate movement plus torsional movement. If you are going to add these two value, you are getting the equivalent movement as 205.36 kilonewton meter. So for this equivalent shear force and equivalent moment, we have to design the beam. We have to find out the flexural reinforcement for this equivalent moment. We have to find out the shear reinforcement for this equivalent shear force. After knowing this equivalent moment, we have to proceed for the flexural design. What does mean by the flexural design? So in this flexural design, we are going to find out the main reinforcement, the reinforcement that will runs along the span of the beam. So that reinforcement we have to find out. So in this flexural reinforcement design, the formula is there: 0.5 FCK divided by Fy inside bracket of 1 minus square root of 4.6 ultimate moment divided by characteristic strength width depth square effective actually multiplied by width and effective depth. If we are going to put all these values in this formula, so we are getting the required area of reinforcement as 1171.7 mm square. After all of this, we have to compare this requirement with the minimum requirement. What minimum requirement is there? If you are going to design any beam, so how much the minimum reinforcement at least you have to provide in the beam? So that I want to check, you have to refer the clause 26.5.1. Go to your IS code, have a look over this. Page number 47. Here it is given the minimum reinforcement in your beam should be calculated by this formula. So if you are going to rearrange this formula, you are getting the value AS minimum equal to 0.85 multiplied by width effective depth divided by yield strength. So if you are going to calculate with this formula and with these values, you are getting the minimum reinforcement required for this beam as 197.455 mm square. Now here you have to compare this minimum reinforcement with the AST required. So among these two values, you have to consider the maximum one, AST required and minimum requirement. You have to compare these two, which one is maximum, that you have to follow. So here AST required is greater than AST minimum. So this much total area of reinforcement we have to provide. So here I have to decide what diameter of bar we have to provide. So I would like to provide the diameter of bar as 20 mm, and the unit area of this 20 mm diameter of bar is 314.16 mm square. Now actual area of reinforcement required divided by unit area of reinforcement, that will give you number of bars required. So here 3.729 number of bars are required. So we cannot provide this number and we cannot provide lower than that of this value. So at least you have to provide more than of this. So next round of value is going to become what? 4 numbers. So here it is written, we are going to provide 4 bars of 20 mm dia. Therefore, ST provided. How much the area of reinforcement we are going to provide? 4 bars of unit area 314.16. Total area of reinforcement that we are going to finally provide 1256.64, and basic requirement was what? 1171. So slightly more than of the required we are going to provide. So that is a good thing. Now I would like to find out how much the percentage of reinforcement is there in respect of its section size of your beam. Overall section size as depth 550, as width 230. Overall section size of the beam, in respect of that, how much the percentage of reinforcement is there. So total area of reinforcement provided finally divided by section size of your beam. So 1256.64 total area divided by size of the beam 230 by 550. So we are getting the percentage of reinforcement provided in the beam as 0.9939%. It is almost 1%. After the complete design for the flexure, in this fourth step we have to do the design for the shear and have to find out the shear reinforcement. Now before getting into the detailed calculation for the shear design, we would like to understand a basic concept for the shear design. So in this figure you can understand that what is the concept of shear design. Suppose a simply separated beam is there which is subjected to uniformly distributed load. So under the application of the loading and based on the support condition, your beam will be subjected to very high intensity of the shear force near its end, near its supports on both sides. So due to very high intensity of this shear force and due to presence of this support condition and due to action of loading, what possibility will be there? There will be the possibility of development of cracks from the edge of the support, from the point of the support, and these cracks may get propagate along the depth of the section. On later stage, these shear cracks will become a cause of complete failure of this beam. So if you would like to control this development of these cracks, you need to provide the additional shear reinforcement. In actual, your concrete is also having capacity to resist the shear force, but that capacity is very small. At initial stage, your concrete is taking the responsibility for resisting the shear forces. But when the capacity of this concrete is going to lose, when concrete is not much enabled to resist this shear force, so at that time we need to provide the additional reinforcement, and that additional reinforcement will be responsible to control the development of the cracks as well as control the propagation of these cracks also. And this vertical reinforcements we are going to call it as shear reinforcement. So how to do the calculation for finding out the how much the shear reinforcement required, what codal recommendations are there, everything we will try to understand in detail. Now first we have to calculate the nominal shear stress that is going to be developed at a critical section. So what does mean the critical section? So the critical section is the section where we are expecting that nominal shear stress will be very high. So suppose this is your critical section. So at this critical section I have to find out how much the nominal shear stress is going to be developed due to action of the shear force. So the formula for calculating the nominal shear stress, that is tau VE, nominal equivalent shear stress I can call it. So VE divided by B into D. So if you are going to put all the values here, so you will get the answer as 2.146 MPa. So this is what the nominal equivalent shear stress. Now I have to compare this nominal equivalent shear stress 2.146 with the value of maximum shear stress. So how much the maximum shear stress capacity? So the formula for calculating the maximum shear stress will equal to 0.63 under root of FCK. So after doing the calculation, we are getting the value as 3.15. Now we have to compare this critical maximum shear stress with the nominal equivalent shear stress. After comparison of these two values, we are getting that nominal equivalent shear stress is less than the maximum shear stress, and that is what expected, because in a situation when nominal equivalent shear stress is going to become more than of maximum shear capacity of the section, at that time you need to revise the section, you need to increase the section size. But in a situation when you are getting nominal equivalent shear stress less than of the maximum shear stress, at that time we can say that that provided section size of the beam is adequate. There is no need to revise the section. But yeah, here it is not decided that whether it is needed to design for shear or not. That is going to be decided by comparison of nominal equivalent shear stress with the critical shear stress. You have to compare these two values. So if you would like to calculate critical shear stress, so you need to know the characteristic strength of the concrete, or in another way you can say that the grade of concrete. So grade of concrete is M25. So accordingly characteristic strength is going to become 25, and percentage of main reinforcement, how much the longitudinal reinforcement you have provided. So earlier we have seen that in our flexural design we have provided the percentage of reinforcement as 0.9939. So we have to take into consideration this percentage of reinforcement also. So just come down and look at this. So it is the percentage of reinforcement provided, and this is the characteristic strength or grade of concrete. So in reference of IS 456-2000, page number 73, table number 19. Have a look over this. Here, for different percentage of reinforcement, their respective shear stresses for different grades of the concretes are available. So here our concern with 0.75 and 1% of reinforcement, because our value is 0.99% of reinforcement is there approximately. So that comes in between these two values. So for 0.75, for M25 grade of concrete, the value is 0.57. For 1% of reinforcement, the value of tau C will be 0.64. So these two value I am going to put here. For 0.75, the value is 0.57, and for 1%, 0.64. So our intention is to calculate the value for 0.9939. So you have to do the linear interpolation, and after doing the linear interpolation, we are getting the value of 0.6383 MPa, that is Newton per mm square. Now I have to compare this critical capacity with the nominal shear. So after comparing these two values, we are getting the nominal equivalent shear stress is greater than that of the critical shear capacity. That's why here it is needed to design for the shear and have to provide the shear reinforcements. Now, after making the decision to go for the shear design, first of all we need to look at IS 456-2000, page number 75, clause number 41.4.3. This clause has stated that when your beam is subjected to shear force as well as torsion together, so formula for finding out the spacing between the shear reinforcement will be this one. And this formula is given in your IS code. Look at that at page number 75. This is the formula for the shear reinforcement calculation when your beam is subjected to torsion as well as shear force. The simplified version of this formula will become SV equal to 0.87 FY ASV D1 divided by TU divided by B1 plus VU upon 2.5. So here most important terms are ASV. This is the area of unit shear reinforcement. This is the D1 and this is what B1. These are the other two dimensions along the width of the beam, along the depth of the beam. We will see how to do the calculation for B1 and D1. Now first I would like to calculate unit area of the shear reinforcement. For that we need to make the decision for diameter of bar and number of legs. So I would like to provide 2-legged vertical stirrup of diameter 10 mm. So unit area of shear reinforcement is going to become number of leg multiplied by unit area. So 2 times 2 legs are there, pi by 4, 10 square, because 10 mm diameter of bar we are going to use. So unit area of this one ring is going to become 157.08 mm square. Now next we have to calculate the dimension along the width, along the depth as B1 and D1. So D1 is going to become what? Overall depth we are having 550 minus effective cover from the top minus effective cover from the bottom. So after doing the calculation we are getting the value as 460 mm. Likewise we have to do the calculation along the width. So along the width, overall depth, overall width is what? 230 mm minus this much width we have to subtract from total width, and this is from both of the side. That's why 2 times multiplied by clear cover plus full shear reinforcement dia plus half of your main reinforcement. So it is giving the value as 140 mm. Now we are having the B1 value, D1 value, ASV value. Put all this value in this simplified formula. After taking all that values in this simplified formula, we are getting the spacing as 144.02 mm. And you are not allowed to provide the spacing beyond of this. That's why we are going to choose the value as 125 mm center to center so that it will be easy to execute on site. But we have to check this spacing with maximum minimum criteria. So with the minimum shear reinforcement criteria, which is suggesting that your spacing in any case should not be more than of this value. So the minimum spacing calculation equation has given in your IS 456-2000. Just look at this. In your IS code, in the same clause 41.4.3, the equation here it is given. So I am going to use this equation to calculate the spacing. So again, put all the values in this equation. We are getting the value of ASV as 190 mm, but we have provided the spacing as 125, so that is okay. Reinforcement will be a little bit closer to each other, so that is good thing. You are going to provide the more reinforcement, but if you are going to increase the spacing between the two shear reinforcement, so that is what critical. So this spacing, your spacing should not be less than of this value. So that is what satisfied. We will proceed with this final spacing. Plus we have to check it with the maximum spacing criteria. In no any case your spacing should be more than of these three values: x1 plus y1 divided by 4 and 300. So here question is that how you can calculate this x1 value, how you can calculate this y1 value. So this is actually the center to center distance between the shear reinforcement along its section. So how I can calculate this? So first y1 is actually from this point to this point, but we already have the value of d1, which is center to center distance between the reinforcement along the depth of the beam. So d1 we are already having. We just have to add half of your diameter of main reinforcement plus half of your diameter of shear reinforcement. If you are going to add these two values from both of the sides, so you will get the value of y1. So I am going to do the same thing. Here it is what? d1 plus 2 times half of your main reinforcement plus half of your shear reinforcement. After doing the calculation, we are getting the value as 490 mm as y1. Likewise, you have to do the calculation along the width. Center to center distance we are having for the main reinforcement. We have to add half of diameter of main reinforcement plus half of diameter of your shear reinforcement to get the value of x1. Now x1 is going to become b1 plus 2 times half of your main reinforcement, half of your shear reinforcement. We are getting the value of 170 mm. Now x1 as 170 mm, x1 plus y1 divided by 4 is going to become 165 mm, and in no any case your spacing should be more than of 300. So these are the maximum criteria. You are not allowed to take the spacing beyond of this. If I am trying to take the spacing 175, that will not be okay. If I am trying to take the spacing 170 also, that is not also be okay. And 300, you are not allowed to provide the spacing beyond of this 300. So we have decided to provide spacing 125. So your 125 is less than of all these three requirements. So overall your spacing is what? Safe, 125 mm center to center distance between the shear reinforcement. So we are going to provide 10 mm diameter of bar, 2-legged vertical strap at a spacing of 125 mm center to center. Now in respect of all these design results, we are going to prepare the schedule. And what schedule we are going to prepare? So in this schedule we have to write the section size. So section size of the beam is what? 230 by 550. Reinforcement we are going to provide as main at its bottom 4 bars of 20 mm dia, and just to tie your main reinforcement or to keep your shear reinforcement in its position, we are going to provide the top reinforcement as 2 numbers as 12 mm dia on top, and shear reinforcement 2-legged vertical strap of diameter 10 mm at a spacing of 125 mm center to center. And you have to prepare the detail also. So in this detail you can see at the bottom 4 bars of 20 mm dia is present, and shear reinforcement is having the spacing as 125 mm center to center, and at the top 2 bars of 12 mm dia as minimum number of bars as provided on the top. This is what section of the beam, and this is what showing the reinforcement detailing. And in 3D view, if you would like to see the provision of the reinforcement, so here at the bottom we have provided 4 bars of 20 mm dia. This is what your longitudinal reinforcement, or I can say the flexural reinforcement, or I can say the main or tensile reinforcement. On the top, 2 tensile or main reinforcement we have provided, but that is for satisfying the codal requirement. At the top, in any case, there should be a presence of 2 number of bars at least. And the spacing of the shear reinforcement is what? 125 mm center to center with a diameter of 10 mm, 2-legged vertical stirrups. So this is what complete scheduling and detailing in respect of your design result. Hope that you all understood how to do the design for your beam. Hello everyone, welcome you all in a new ISO certified live training program, design of substructure using CSI Safe, Excel and manual. In this training program, you will learn all about the concept of substructure design, commands in CSI Safe software for the substructure design, validation of CSI Safe result with your manual and advanced Excel sheets. This training program will cover 4 real life projects. In the first and second, we will cover all the types of isolated foundation in CSI Safe software. In the third real life project, we will cover the raft foundation. And in the fourth real life project, there will be the coverage of pile and pile cap design of basement wall. And at the end of this training program, we will learn how to prepare the final design sheet for the site execution. Have a look over the features of this training. Daily live classes conducted by experts. Recording of every session. Can interact with expert anytime. Exposure to real practice. ISO certification of training. It's 5-star rated training program. Till now more than 1,000 participants have benefited from this training program. Now you are the next.